Hello, everyone. In this video, we explore the first of two important applications of the spectral theorem and the diagonalization of symmetric matrices with orthogonal matrices. The first application that we talk about today is called spectral decomposition. What we saw last time is that if a matrix A is symmetric, then we can diagonalize it with orthogonal matrices. So we can write it as PDP transpose, where P is orthogonal. And in other words, when we write this down explicitly, we see that the columns of P are going to be given by eigenvectors, U1 through UN, which will be orthonormal. So this is an orthonormal basis of eigenvectors that make up the column P. The diagonal matrix D will contain the corresponding eigenvalues and nothing of the diagonals. And then allow me to write this matrix P transpose. I'll write it with the same vectors, except I'll transpose them because now I want to see them as rows. So here we see the eigenvectors as row vectors. Okay, so I expanded this out, but I want to compute a little bit of what's going to happen here. Well, if you do the computations, then you'll see that, well, yeah, I mean, the way that this can be computed is by just observing that the lambdas, the eigenvalues here, will just rescale all of the rows that happen on this side. So if you just give it some thought and try to compute it out, you get that, oops. The entries of this matrix are just given by this following, I mean, this sums over here. You will get at some point U1 that multiplies U1 transpose and the eigenvalue lambda 1, and then U2 will multiply the eigenvalue lambda 2, and so on and so forth. I think maybe the best way to see this is to compute first the multiplication of this vector with this matrix over here, column by column, and then use the orthogonality of the vectors involved. So, I mean, it takes some steps that I don't want to get into detail too much about how to get this writing, but we'll see it in an example. So what you get out of this is exactly this expression. Lambda I times UI transpose. Now, these UI transpose are very important, and they deserve a little bit more thought than what we've given them so far. First of all, let's just observe their size. UI is a n-dimensional column vector, so it has n rows and one column, and UI transpose has one row and n columns because it's a row vector. So the output of those is an n by n matrix. In other words, UI transpose is an n by n matrix. So it's legitimate for us to wonder what this matrix does. And well, let's try. What happens when I multiply UI transpose with any vector v is the following. You get UI transpose v is nothing but UI dotted with v. But I can rewrite this as follows, and maybe we'll recognize this for being on a certain familiar form. So I'll write UI.v multiplied by UI, and then I can allow myself to divide by the length of UI squared, because UI is the column of an orthogonal matrix. It's an orthonormal eigenvector. In particular, this is equal to 1. But the reason why I divide that by that factor is that you can probably recognize here the projection of V onto the vector UI. That's what UI transpose does as a matrix with matrix multiplication. That's what's written here. Multiplying V by UI transpose projects it down onto UI. In other words, the matrix PI that we, if we call PI the matrix UI transpose, this is a projection matrix to the subspace which is spanned by the eigenvector UI. This is the spectral decomposition. It's as an application of our spectral theorem, we get a decomposition of the matrix A. Remember that that's where we started. We wrote A as PDP transpose, and then we expanded out this product into this writing down here. So we can write A as the sum of lambda I times pi, where lambda i's are the eigenvalues and pi's are the projection onto the corresponding eigenvector. Let's have a look at one example. I'll take this matrix here. A is 1/13, these entries, -7, -48, -48, 33. I computed before that there's two eigenvalues, 5 and -3, and I found the two eigenvectors, U1 and U2. I made sure that they're orthogonal and they're normal to one another. So essentially what we did here is to find the matrices D and the matrix P of the diagonalization. So the ones that realize A, PD, PD. So let's write down the spectral decomposition of A. The spectral decomposition will be given by lambda 1 times projection matrix 1 plus lambda 2 times projection matrix 2. Let's compute the projection matrices. If I do U1 times U1 transposed, I get the following. I get 1/√13 times 2 minus 3, and I multiply this by 1/√13, and I transpose the vector, which is 2 minus 3. So the end result is 1/√13, and then this should be a 2 by 2 matrix. Well, let's see. First row, first column, we get 2 by 2. That's a 4. First row, second column is 2 by 3, -6. -3 times 2, it's -6. -3 times -3 is 9. So that's my first matrix. 1/13, 4 minus 6 minus 6, 9. Let's have a look at P2 and do the same computation. I'll have to do U2 times U2 transpose. So as before, those are both divided by 1/√13. So I'll get 1/13 in front, and I'll multiply 3, 2 times 3, 2 transposed. So I get 1/13, and here I get 9, 6. That's another 6, 2 by 3, and then 4. Okay. We can double check how to write A now. So A will be lambda 1 times P1. Lambda 1, I remind you, is 5. So this is 5/13 times 4 minus 6 minus 6, 9. And then we have plus, well, the other eigenvalue is -3. So I get -3/13, 9, 6, 6, 4. And if we, so this is the spectral decomposition of A, but if we wanted to check that this is true, we could go on doing this computation and get back A. Why don't do that? This is 1/13, and then we have 5 by 4 is 20 minus 27 up here. Then we have 5 by -6 is -30 minus 18. And here also we get -30 minus 18. And the last one is 5 by 9, which is 45 minus 12. And I believe that's exactly A. You go back and you check the entries of A, that's exactly what you get. Okay, but here, well, I mean, the spectral decomposition is here. It's lambda 1 P1 plus lambda 2 P2. Okay, let's have a look at some more properties of these projection matrices. They have an important role, so it's good to think about them for a little bit. The first property is that the rank of these projection matrices is equal to 1. The reason why that is that if I apply them to a vector by the computation we did above, I get ui.v times ui. In other words, this is just a constant. So the image of the output of this matrix multiplication is generated by one vector, which means that its column space spans the image, which is just one-dimensional, and so the rank is 1. This other property is maybe a little bit new. These matrices are what are called idempotent matrices, meaning that if I do it twice, it's the same as doing it once. So once I did it once, I can't project further. It makes sense. If you think about projecting a vector onto a subspace, if you do that projection twice, you end up always in the same place. So it makes sense that projections are idempotent, but let's see how to make sense of these properties. Well, what we did was that we can use these following two facts. If I do pj times v, that's just a multiple of uj. And what we know is that ui and uj are orthonormal. So their dot product is 0 when I is different from j, and 1 when I is equal to j. So when I piece these two things together, I can compute pi of pj of v to get, well, by this fact here, I get that this is pi of a certain constant times uj. So now I'm looking at constant times ui dot uj times ui, because that's what pi of uj is. Okay, well, but then what does this mean? You'll see that ui times uj could be 0. I mean, if I is different from j, that's 0. So this is, well, maybe I'll write it down here. This is 0 if I is different from j. If I is j, this is just c times ui, but c times ui is equal to pi of v. But if I is equal to j, pi of v is pj of v. So, yeah. Doing pi pj of v when I is equal to j is the same as doing pi of v. It's the same as doing pj of v as well. Only in the case in which I is equal to j. Okay, with the same reasoning, we see that if I try to project one of the eigenvectors, I get back itself if I project onto the same eigenspace. So pi ui is ui, but pi uj is 0. It's the same sort of computation. If I compute pi times uj, I get ui dot uj in the direction ui, but ui dot uj, that's, well, it's 0 or 1. So when I is equal to j, this becomes 1 times ui. And when I is different from j, this becomes ui dot uj, which is 0 times ui. So we get 0 out of that. Okay, that's it for the spectral decomposition. The next time we'll see another application, which is the singular value decomposition.